Welcome back. In this video, you'll learn about power series and how to find the radius and interval of convergence. Let's get to it. All right, so a power series is an infinite series that involves a variable x raised to some power. Right, and so here we have the simplest form of a power series. We have the sum from n equals 0 to infinity of some sequence a sub n multiplied by x raised to the power n. All right, and so we call it a power series because it is a series where we have a variable raised to a power. And so if we were to look at the first couple terms of this power series, starting with n equals 0, our first term would be a sub 0 times x to the power of 0. Then if we looked at the next term, when n equals 1, we'll have plus a sub 1 times x to the first power. And then we could look at the next term when n equals 2, and we'd have plus a sub 2 times x to the second power, or x squared. And then we could continue on from there and add more terms of the power series. And so if we were to simplify, x to the power of 0 is just equal to 1. So this is equal to a sub 0 plus a sub 1 times x to the first power plus a sub 2 times x squared, and so on. All right, and so like I said, this is the most basic form of a power series. Specifically, we would call this a power series that is centered at the origin or centered at 0. All right, and the reason we say that it's centered at 0 is because there's nothing being added or subtracted to x. We just have x to the power of n. But the general form of a power series will look like this. Instead of having just x to the power of n, we will instead have x minus some constant c, and that whole quantity will be raised to the power of n. Everything else in the power series remains the same. Okay, and so while this basic form of a power series up here is said to be centered at 0, this form is said to be centered at c, and c once again is a constant. Right, so if c was equal to 0, you would have x minus 0, and so that would just be x to the power of n, which is what we have up here. Okay, and so the first couple terms of the general power series will look like this. Our first term will be a sub 0 times x minus c to the power of 0. Right, we're starting with our term where n is equal to 0. Then we'd have our next term where n equals 1, so we'd have plus a sub 1 times x minus c to the power of 1. And then we could have another term when n equals 2, where we'd have a sub 2 times x minus c squared. And we could continue to add more terms from there. And so if we were to simplify, anything to the power of 0 will be 1. So we have a sub 0 times 1. And so this is equal to a sub 0 plus a sub 1 times x minus c to the first power plus a sub 2 times x minus c squared, and so on. All right, and so the general form of a power series is a power series centered at the value of c. Okay, so for example, if we had x minus 2 to the power of n within our power series, we would say that that power series is centered at 2, right? 2 is taking the place of c. Or for another example, if we had x plus 3 to the power of n within our power series, then we would say that the power series is centered at negative 3, right? Because the form is x minus c, and so if we have x plus a constant, in order for that plus to be there, the value of c would need to be negative, because when you subtract a negative value, it becomes positive. All right, so if you found this quantity within a power series, you would say that that power series is centered at negative 3. Okay, and so now that you are familiar with the general form of a power series, as well as the simplest form of a power series, let's take a look at a couple examples of some power series. Okay, so here's our first example of a power series. We have the sum from n equals 0 to infinity of x to the power of n divided by n factorial. Now, right away, you can identify that this is a power series because you have a variable x raised to the power of n. The moment that you see x, a variable, within your series, you know you're working with a power series. Okay, and so if we were to write out the first couple terms of this series, this is what it would look like. Starting with n equals 0, we would have x to the power of 0 divided by 0 factorial. Then we would add that to when n is equal to 1. So we would have x to the power of 1 divided by 1 factorial. And then when n equals 2, we'll have plus x squared divided by 2 factorial. And then let's do one more. When n equals 3, we'll have x cubed divided by 3 factorial. And we can continue on from there. But to simplify, x to the power of 0 is just 1, and 0 factorial is also equal to 1. So this first term is 1 divided by 1, which we can just rewrite to be 1. And that would be added to x to the first power divided by 1 factorial. And we know that 1 factorial is just 1. And so we have x divided by 1, which is just x. And then from there on out, we would have x squared divided by 2 factorial. And 2 factorial is equal to 2. So we'll just rewrite that to be 2. And then we'd add that to x to the third power divided by 3 factorial. And 3 factorial is 1 times 2 times 3, which is equal to 6. And we could add on our terms from there. All right, and so these would be the terms of this power series. And it's important to note here that this power series is a power series that is centered at 0, right? Notice that the x being raised to a power of n does not have a constant added or subtracted to it. It's just x to the power of n. All right, so the value of c would be equal to 0, which means that our power series is centered at 0. Now for another example, let's take a look at this power series. We have the sum from n equals 0 to infinity of negative 1 to the power of n times the quantity x minus pi to the power of 2n plus 1 divided by 2n plus 1 quantity factorial. Okay, so once again, this is a power series because we have a quantity with x raised to some power. All right, however, this time, this power series is not centered at 0. Notice that we have x minus pi, right? The quantity that has x within it that's being raised to a power includes pi being subtracted from that x. And so this power series is centered at pi. Okay, so just make a note that this power series was centered at 0, but this power series is centered at pi. Okay, now if we were to look at the first couple terms of this power series, they would look like this. Let's start with n equals 0. We would have negative 1 to the power of 0, which would just be 1, and so we don't need to worry about that part. But then for the rest of our expression, we will have x minus pi to the power of 2 times 0 plus 1 divided by 2 times 0 plus 1 factorial. Then we'd have another term when n equals 1. In this case, we would have negative 1 to the power of 1 times x minus pi to the power of 2 times 1 plus 1 divided by 2 times 1 plus 1 factorial. All right, and we could add more terms on from there, but I kind of ran out of space, so we're just going to work with the first two terms here, and if you wanted to see what some of the others would look like, you can try to write them out yourself. But if we simplify what we have, this power here is 2 times 0, which is 0 plus 1. So we just have this quantity to the power of 1. So we would have x minus pi, and that will be divided by 2 times 0 plus 1 factorial. And 2 times 0 is 0, plus 1 is 1. So 1 factorial is 1. So we just be dividing by 1. So we don't really need to write that. We can just have the quantity x minus pi. So I'll write that down. And then our next term, we have negative 1 to the power of 1, so that will be negative 1. In fact, this power series is going to alternate between being positive and negative with each term because of that negative 1 to the power of n. So instead of having plus here, let's just account for that negative and subtract this term, and then we'll have x minus pi to the power of 2 times 1, which is 2, plus 1, which is 3, so we'll have the power of 3, and that will be divided by 2 times 1, which is 2, plus 1, which is 3, factorial. And 3 factorial is equal to 6. Okay, and we could add more terms from there, but you kind of get the idea of what the terms look like for a power series. And so now that you've seen some examples of actual power series, what do you notice about the resulting terms from these series? Well, what's actually going on here is as you write out the terms of the series, you are actually creating a function of x, right? For this power series, our terms are 1 plus x squared divided by 2 plus x cubed divided by 6. As we add more and more terms, we are building some function of x. And the same is going to occur for this power series. We have a term that includes x within it, and then we're subtracting another term that also includes x, and then we're going to be adding more terms and subtracting more terms for this power series that are going to include a variable x. And so a power series is actually creating a function of x. Okay, and so that's going to be one of the most important takeaways from this video, is to make that connection between a power series and a function. A power series is going to form a function. And so let's take a closer look at what that means for a power series and the function that it represents. Okay, so we've established that a power series creates a function f of x, and because of that, we would say that f of x is equal to that general form of a power series, right? F of x will be equal to the sum from n equals 0 to infinity of a sub n times the quantity x minus c to the power of n. All right, and so if we're thinking about a power series as a function, what has to be true about this series in order for a value of x plugged into our function to result in some output value? Well, remember, if a series converges, that series will have a sum. And so you would say that that series is equal to the value of that sum, right? But if a series diverges, it does not converge to a specific value, then the series isn't equal to any value. It's an undefined value. And so what's actually going to happen for a power series is, depending on the value of x, that power series could converge or it could diverge. And depending on whether it converges or diverges for a specific value of x decides whether the function is defined for that value of x. If we have a value of x that makes the power series convergent, then the output of the function will be the sum of that convergent series. But if the power series diverges for a value of x, then it doesn't have a sum, and therefore the function doesn't have an output for that value of x. The value is undefined. Okay, so the function, this function right here, f of x, will only be defined for a domain of x values for which the power series converges. Okay, and so now let's take a look at a power series that we can represent as a function, and how the convergence of that power series is going to affect the domain of that function. Okay, so here's our example. We have a very basic power series here. In fact, this might be the most basic power series you will ever see. We just have the sum from n equals 0 to infinity of x to the power of n. This is very clearly a power series because we have the variable x raised to the power of n. Okay, so the first couple terms of this series would be x to the power of 0 plus x to the power of 1 plus x squared plus x cubed, and so on. All right, and x to the power of 0, of course, is equal to 1, and so we have 1 plus x squared plus x cubed, and so on. All right, and so what I want you to notice about this power series is it's actually in the form of a geometric series, right? If you remember, a geometric series looked like this. We had the sum from n equals 0 to infinity of some constant a times the common ratio r to the power of n, right? And so that is a geometric series. I just want to label that. And so if we compare this form to our power series, note that x would be the value of r, right? Our common ratio is raised to a power of n, and x is raised to a power of n. And our constant multiple a would just be equal to 1, since we only have x to the power of n. And so if we view this as a geometric series, we would have 1 times x to the power of n. Okay, and so keeping that in mind, remember what we know about the convergence of a geometric series. We said that a geometric series converges if the absolute value of r is less than 1. And so if we're saying that for this power series, that it is a geometric series where a is equal to 1 and r is equal to x, then this power series will converge if the absolute value of x is less than 1, right? X is our value of r, and so if the absolute value of r or the absolute value of x is less than 1, then our power series here would converge. And another way to write that, if we were to remove the absolute value bars, is to say that for values of x greater than -1 but less than +1, this power series would be a convergent series. Okay, but we're not done yet. Remember that we also know how to calculate the sum of a geometric series, right? We know that the sum of a convergent geometric series is a divided by 1 minus r. And so if we use this sum formula for our power series, where a is equal to 1 and r is equal to x, then the sum would be equal to 1 divided by 1 minus x. And this right here, 1 divided by 1 minus x, is the sum for this power series for any value of x. And so what this actually represents is the function that is created by this power series, right? So f of x is equal to the sum from n equals 0 to infinity of x to the power of n. This power series represents a function f of x, and the sum of that series is 1 divided by 1 minus x, because this is in the form of a geometric series, and so the function f of x that this power series represents is 1 divided by 1 minus x. However, because this power series only converges for values of x between -1 and +1, this function is only defined for those values of x. All right, so this series represents this function, but only for x greater than -1 and less than +1. And you could also represent this with interval notation of -1, 1. Okay, and then one more thing to point out here is if you go back to our original power series, note that we would say that this power series is centered at 0, right? Because we just have x raised to that power of n. There is no constant being added or subtracted to x, and so it's centered at 0. And what I want you to notice about this interval is that that value of 0 that our power series is centered at is in the center of this interval, right? The value of 0 is right in the middle between -1 and +1. All right, so hopefully that makes a little more sense. That's why we say that this type of power series would be centered at 0, because the interval of the values of x that it's going to be convergent for is going to have 0 at its center. Okay, and since that center is at 0, and each of the endpoints, -1 and 1, are both one value away from that center of 0, we would say that the radius for this power series is 1. The values of x for which it is convergent for has a radius of 1 from that center. All right, and we'll talk about the radius more in a little bit. Okay, so hopefully this example helps you to see how a power series can represent a function for a domain of x values for which that power series is convergent for. All right, and so this leads us into the main focus of what we're going to be doing with power series. What we want to be able to do for a power series is determine the interval of convergence for any particular power series, not just this power series that happens to be a geometric series, but any power series, as well as the radius of that interval of convergence. Okay, and so that's what we are going to look at next. All right, now before we talk about determining the convergence for a power series, or more specifically the interval of convergence, I wanted to quick make you aware of a couple things here. The first thing is that for a general power series that represents a function, the value of the function when x equals c is just going to be equal to the term a sub 0. Okay, because when x equals c, this quantity right here will be c minus c, and so we would have 0 to some power, but 0 to any power is just going to be 0. And so all of the terms after the first term are just going to be 0, and so when you evaluate the function at x equals c, you're just going to get a sub 0. Okay, and that's important because what it says about the function that's represented by the power series is that that function is always defined for that value of x equals c. And as a result of that, the domain of the function will always be an interval with x equals c at the center. That's why we've been saying that a power series is centered at that value of c. Okay, so keeping all of that in mind, now let's talk about the convergence of a power series. All right, so a power series of this form could converge in one of the following three ways. It could be convergent for only one value, and that is at x equals c. In that case, the radius for the interval of convergence is just 0, and we represent that with capital R. We say that the radius of the interval of convergence is equal to 0 because the interval of convergence really doesn't exist. We're just saying that for when x minus c is between 0 or just equal to 0, that our power series converges. All right, so that's the first way that a power series could converge. It might only converge for one value of x, that being x equals c, but it could also converge for all values of x. In this case, the radius for the interval of convergence would be infinity, because the interval of convergence will be from negative infinity to positive infinity. For any value of x minus c between negative infinity and positive infinity, that power series would be convergent. And we could represent that interval of convergence by writing it in interval notation where we have negative infinity, comma, positive infinity. All right, and then finally, a power series could also converge for some values of x within a certain radius. The absolute value of x minus c will be less than the value of some radius r. And what this means is that the values for the absolute value of x minus c greater than that radius will result in the power series diverging. Okay, so in this case, the interval of convergence will be from negative r, or the negative version of the radius, to the value of the radius. Okay, and so then if we added c to both of these sides, then your interval of convergence would look like this. The power series would converge for values of x between c minus the radius and c plus the radius. And we could also write that in interval notation like we have right here. Okay, so what we would be saying for this third case is that our power series converges, or the function that it represents is defined for values of x between whatever these two values are, depending on what c and r are equal to. Okay, and then one more thing I want you to notice here is that we only have these less than signs, and we have open brackets for our interval notation. It's possible that our power series will also be convergent for one or both of those endpoints. And so what we're going to have to do is actually check the convergence of our power series for each of those values of x manually to decide if we should have closed brackets to include those endpoints as values of x that make our power series convergent. Okay, so that's a lot to soak in. It might seem fairly complicated at this point, but once you actually see our method of determining the convergence of a power series, these three ways that it could converge are going to make a lot more sense. And so with that, let's take a look at our first example of determining the radius and interval of convergence for a power series. Okay, so here's our first example. For this series, we have the sum from n equals 0 to infinity of n factorial times x to the power of n. All right, so right away, we know that we are working with a power series because we have x raised to a power of n within that series. All right, and so what we want to do for this power series is find an interval for values of x that make this power series convergent. And the way we're going to do that is use one of our convergence tests that we have learned previously. In fact, for pretty much every single power series we're going to work with, we are going to make use of the ratio test. And the reason we use the ratio test is because the ratio test tells us when a series converges or diverges. And so if you don't remember, the ratio test says this: for a series where we have the sum of a sequence a sub n, if the limit as n approaches infinity of the absolute value of the ratio between a sub n plus 1 and a sub n is equal to some limit less than 1, then the series converges absolutely. Or in this case, we're just going to say it converges. But if that limit was greater than 1, or it was equal to infinity, then that series diverges. And then finally, if that limit was equal to 1, the test is inconclusive. But we're not really worried so much about this last conclusion. If you look at the first two here, you can see that for a series, we know that it's going to converge when the value of this limit is less than 1, and we know it's going to diverge when the value of that limit is greater than 1, or it's equal to infinity. Okay, and so because we can make that comparison between the value of the limit and whether it's less than or greater than 1, or if it's just equal to infinity, that is going to allow us to create an interval of values of x for which our power series converges. And so let me show you what I mean. Let's go back to our example. If we use the ratio test for this series, we first need to identify a sub n and a sub n plus 1. In this case, a sub n will be equal to n factorial times x to the power of n, and a sub n plus 1 will be equal to n plus 1 factorial times x to the power of n plus 1. We just replaced each of these n's with n plus 1. And so now we're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. So we're going to have n plus 1 factorial times x to the power of n plus 1 divided by a sub n, which is n factorial, times x to the power of n. Okay, and so now what we want to do is just simplify this limit up to a point where we can evaluate it. And so what I'm going to do first to simplify this is break up this power for x. We have x to the power of n plus 1. We can break that up to be x to the power of n times x to the first power. And so let me do that. We'll have the limit as n approaches infinity of the absolute value of n plus 1 factorial times x to the power of n times x to the first power. And that will be divided by n factorial times x to the power of n. Okay, now another thing that we can simplify is this n plus 1 factorial. We can rewrite n plus 1 factorial to be equal to n plus 1 times n factorial, right? The reason we can do this is because let's say we have 4 factorial. That would be equal to 4 times 3 times 2 times 1, but we could also say that that's equal to 4 times 3 factorial, right? Because 3 times 2 times 1 is 3 factorial. So we could rewrite 4 factorial to be 4 times 3 factorial. We have the value of that factorial times 1 less than that value factorial. Okay, so n plus 1 factorial would be equal to n plus 1 times 1 less than that factorial, right? N is 1 less than n plus 1. So what we can do is rewrite this n plus 1 factorial to be n plus 1 times n factorial. And now you can see that this n factorial will cancel out with this one in the denominator, and that this x to the power of n will cancel out with this x to the power of n. And so what we're left with will be the limit as n approaches infinity of the absolute value of n plus 1 times x. All right, now at this point, these absolute value bars only need to be around x. They don't need to be around n plus 1 because that is always going to be positive. All of our values of n are positive because we're looking at values of n from 0 to infinity. And so I'm going to rewrite this limit to be the limit as n approaches infinity of the absolute value of x times n plus 1. Okay, and so now if we look at this limit as n approaches infinity, what is going to happen to this expression? Well, the only n we have is right here. And so as this n gets larger and larger, and we're adding 1 to it, this whole quantity is just approaching infinity. And so you could say that this limit is equal to the absolute value of x times infinity. Okay, and so if this is the value of our limit, the absolute value of x times infinity, this is going to be equal to infinity for almost every single value of x, right? If x is equal to 2, 2 times infinity, we would say is still infinity. 3 times infinity, still infinity. Negative 4, the absolute value of that would be positive 4. 4 times infinity is still infinity. However, if x is equal to 0, then we have 0 times infinity, which will be 0. Okay, so for every single value of x, except for x equals 0, this limit will be equal to infinity. All right, and don't worry about 0 times infinity being an indeterminate form, because in this case, that's not what we would be working with. An indeterminate form occurs within a limit where you have two different parts where one is approaching infinity and the other is approaching 0. In this case, this value of x would just be 0. It's not approaching 0. We're saying that when x is equal to 0, that 0 times infinity is 0. Okay, so at this point, we're not working within a limit anymore. Our limit was for n as it approaches infinity, and so it doesn't affect x in any way. Okay, but anyway, the conclusion we came to is that when x doesn't equal 0, the limit is equal to infinity. And when our limit for the ratio test is equal to infinity, it tells us that our series diverges. All right, so our series diverges when x doesn't equal 0. But when x does equal 0, then the limit is equal to 0, which is less than 1, and so from the ratio test, we can conclude that our series converges when x equals 0. And so we'll say converges. All right, and so what we just found here is that this power series is only a convergent series when the value of x is 0. There really isn't an interval of convergence for this series. It's just convergent at one specific value of x, which happens to be the value of c, right? This power series is centered at 0 because we just have x raised to a power of n. We don't have x minus 2 to the power of n or x plus 3 to the power of n. We just have x to the power of n. This power series is centered at 0, and we just found that it only converges when x is equal to 0 or when x equals c. Okay, and so this was the first way that a power series could converge. If you remember from our chart of the 3 different ways that it could converge, the first one was that the power series could converge at just the value of c, and that is what we found here. In this case, it's only convergent for one value, and so the radius for the interval of convergence is equal to 0, and that's actually going to be our final answer here. Because the radius is equal to 0, we really don't have an interval of convergence. And so between the radius being equal to 0 and our statements for when this power series converges versus diverges, this is all the work that we can do for this example. Okay, let's look at another example. Okay, so here's our next example. This time our series is the sum from n equals 0 to infinity of -1 to the power of n times the quantity x plus 1 to the power of n divided by 2n factorial. All right, so once again, this is a power series because it includes the variable x raised to some power. Now in this case, we have x plus 1 raised to a power, and so this is a power series that is centered at -1, right? If that quantity is in the form of x minus c, and we have x plus 1, then c must be equal to -1, because x minus -1 would be equal to x plus 1. Okay? That's not really all that important to determining the convergence of our series, but I just wanted to point that out, that this is a power series centered at -1. Okay, and so now, in order to find the interval of convergence for this power series, we want to use the ratio test. So we need to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, now in this case, notice that both of those terms are going to be rational expressions, or they're going to be fractions, because a sub n would be this expression right here, and a sub n plus 1 is also going to be a rational expression like a sub n. And so because of that, instead of writing out a large complex fraction of a fraction divided by a fraction, what I'm going to do is write out a sub n plus 1 and then multiply it by the reciprocal of a sub n, which is the same as dividing by that fraction, right? Dividing by a fraction is the same as multiplying by its reciprocal. And so here's what our limit will look like. We'll have the limit as n approaches infinity of the absolute value of a sub n plus 1, which is going to be -1 to the power of n plus 1 times x plus 1 to the power of n plus 1 divided by 2 times n plus 1 factorial. And we're going to multiply that by the reciprocal of a sub n, which is the same as dividing by a sub n. And so if this right here is a sub n, we can find the reciprocal by flipping the numerator and denominator. So we'll have 2n factorial divided by -1 to the power of n times x plus 1 to the power of n. Okay? And so now what we want to do is simplify our limit here so that we can evaluate it to determine our interval of convergence. All right, and so the first thing I notice here is that these absolute value bars are going to eliminate this -1 to the power of n plus 1 and this -1 to the power of n. Both of those expressions can only be one of two values. They'll either be +1 or -1, and so the absolute value of both of those values is +1. So those parts are just going to be eliminated. They're just equal to 1. And then the next thing I want to do is simplify this factorial a little bit. We have 2 times the quantity n plus 1, right? We just replace this n with n plus 1 for the a sub n plus 1 term. And so I want to simplify that a little bit. 2 times n is 2n, and 2 times 1 is 2. So what we really have here is 2n plus 2 factorial. And so I'll write that in. Okay, and then one more thing before we rewrite our limit. I'm going to split this power. We're going to have x plus 1 to the power of n times x plus 1 to the power of 1. All right, so I'm going to do that when I rewrite our limit here. We're going to have that this is equal to the limit as n approaches infinity of the absolute value of x plus 1 to the power of n times x plus 1 to the first power times 2n factorial divided by 2n plus 2 factorial times x plus 1 to the power of n. All right, now you notice I left some space here. That was on purpose, because what I want to do next is rewrite this factorial. We can simplify this so that our factorial will cancel out with the factorial in the numerator, right? Similar to our last example, we can rewrite a factorial by taking that quantity and multiplying it by a value 1 less factorial, right? So in this case, 2n plus 2 factorial will be equal to 2n plus 2 times 2n plus 1 factorial, but that doesn't quite match up with what's in the numerator here. So if we extend it one more term, we would multiply by 2n factorial, right? We just decrease this value by 1 each time and tag on that factorial at the end of the last value. All right, so we can rewrite this to be these three values, and so I'll do that. We will have 2n plus 2 times 2n plus 1 times 2n factorial. All right, and so these two factorials are going to cancel out. And then notice that we have x plus 1 to the power of n in the numerator and denominator. So those are going to cancel out. And now we're just going to be left with x plus 1 in the numerator and these two quantities in the denominator. And so this is equal to the limit as n approaches infinity of the absolute value of x plus 1 divided by 2n plus 2 times 2n plus 1. Okay, and so now if I clean up my work, we can rewrite this limit again. These absolute value bars are only needed around x plus 1 because that could be negative or positive. We don't know. We're trying to figure out what values of x will make this series convergent. And so we need to keep those absolute value bars there, but we don't need them for the denominator because all of our values of n are going to be positive. And so I'm going to split up this limit to look like this. We'll have the limit as n approaches infinity of 1 divided by 2n plus 2 times 2n plus 1 times the absolute value of x plus 1. Okay, so I just kind of separated both parts. We have our expression with all of our n's, and then we have the absolute value of the part that has x in it. Okay, and so now if we take the limit as n approaches infinity of this expression, we don't need to worry about this part because there's no n's within it. This is not affected by this limit. And if we look at this denominator here, as these n's would approach infinity, this denominator is just going to increasingly get bigger and bigger. And so we have 1 divided by infinity, and we would say that 1 divided by infinity is going to approach 0. As that denominator gets bigger, this value of 1 divided by that denominator will get closer and closer to 0. So this limit is equal to 0 times the absolute value of x plus 1. All right. Now, anything times 0 is going to be 0, right? And so this absolute value of x plus 1 is going to be completely eliminated. It doesn't even need to be there, all right? So this limit is now just equal to 0 because anything times 0 is 0. And so what we find here is that this limit for the ratio test for our power series is equal to 0, which is less than 1, which means that our series is a convergent series. In this case, the power series is going to be convergent for all values of x. It doesn't matter what value of x we use for this series. The ratio test says that this limit will always be equal to 0, which means that the series will always converge. All right, so in this case, our interval of convergence is going to be from negative infinity to positive infinity, right? For any value of x from negative infinity to positive infinity, this power series is a convergent series. And then along with that interval of convergence, we would say that the radius is equal to infinity. Okay, and so that is the final answer for this example. We have determined that this power series is convergent for this interval from negative infinity to infinity, which means that the radius is equal to infinity. All right, and so this was an example of the second way that a power series could be convergent, if you remember from our 3 different ways. The first way was that it would only be convergent at one value of x. The second way was that it would be convergent for all values of x. That's what we just found here. And now finally, we're going to look at an example where our power series will converge in the third way. This next power series is only going to converge for specific values within a certain radius. So this next time our radius is not going to be 0 and it's not going to be infinity, it's going to be some other finite value. And so let's take a look at that example next. All right, so here's our last example. This time our series is the sum from n equals 1 to infinity of x to the power of n divided by n. All right, and so this is a power series because we have x raised to a power of n within that series. All right, in this case, our series is centered at 0 because we just have x raised to the power of n. There is no constant being added or subtracted from x, and so the power series is centered at 0. All right, so keeping that in mind, let's use the ratio test to determine what the interval of convergence will be for this series. All right, so we're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, okay? And so that will be equal to the limit as n approaches infinity of the absolute value of a sub n plus 1, which will be x to the power of n plus 1 divided by n plus 1, right? This is a sub n, so a sub n plus 1 will add 1 to each of these n's. So we have x to the power of n plus 1 and n plus 1 in the denominator, okay? And then we're going to multiply this by the reciprocal of a sub n, and that will be the same as dividing by that fraction, okay? So a sub n is equal to x to the power of n divided by n. So if we want to divide by that, we can multiply by the reciprocal, which will be n divided by x to the power of n. We just flipped the numerator and denominator to get that fraction. Okay, now to simplify, we can split up this power for x. We have x to the power of n plus 1. That would be the same as x to the power of n times x to the first power. So I'll rewrite this. We'll have the limit as n approaches infinity of the absolute value of x to the power of n times x to the first power times n divided by n plus 1 times x to the power of n. Okay, and so now we can see that this x to the power of n will cancel out with the x to the power of n in the denominator, and that's all that cancels out. And I can also erase this first power here. X without an exponent is x to the first power. And so if we rewrite our limit, this will be equal to the limit as n approaches infinity of the absolute value of x times n divided by n plus 1. All right, now at this point, the absolute value bars are only going to affect x because n and n plus 1 are always going to be positive since n is only defined for positive values from 1 to infinity. So if I rewrite this again, we'll have the limit as n approaches infinity of n divided by n plus 1 times the absolute value of x. Okay, and so now let's take the limit as n approaches infinity of this expression. We have a rational expression where the numerator and denominator are just algebraic expressions, right? We have n to the first power and n to the first power plus 1. And so a quick way to evaluate this limit as n approaches infinity is to look at the highest power of n in the numerator and denominator. In this case, that highest power of n is 1, right? We have n to the first power in the numerator and n to the first power in the denominator. And since those highest powers are equal, this limit as n approaches infinity will be equal to the ratio of those coefficients for those two terms with n to the first power. So the limit will be equal to 1, which is the coefficient of this n, divided by 1, which is the coefficient of this n. And so this is equal to 1 times the absolute value of x. Remember, this is not affected by the limit because the limit is just as n approaches infinity, not x. And so this remains the same. So we just have 1, which is the limit of this expression, times the absolute value of x. All right, and so we could remove that 1, and this would just be equal to the absolute value of x. So I'm just going to write that a little closer. We'll have the absolute value of x. And so in this case, our limit for the ratio test is equal to the absolute value of x. And so we don't know what x is, but we know that whatever this is equal to, for this limit, it needs to be less than 1 in order for our power series to converge, right? That's from the ratio test. As long as the value of this limit is less than 1, our series converges. And so we can set the absolute value of x to be less than 1, and solving for x will tell us what values of x make this power series convergent. All right, but before we do that, I just want to point out that as soon as you get to this point in your work for the ratio test for a power series, where you have the absolute value of whatever expression is being raised to the power of n in your power series, right? In this case, we just have x to the power of n. As soon as you have that x in absolute value bars less than some value, whatever that value is less than, that is going to be your radius for the power series. All right, and just as another example, let's say that instead of x to the power of n, we had x plus 2 to the power of n, meaning that c would be equal to negative 2. Instead of having the absolute value of x at this point, what we would see is the absolute value of x plus 2 less than 1. And if you solve that in your work, that would still mean that the radius is equal to 1, okay? So once you see that that part being raised to the power of n, x plus 0 or x plus 1, x plus 2, x minus 3, whatever, once you see that within absolute value bars and you set it to be less than 1, that is going to be the radius for your power series. Okay, and so the way that would change from being just 1 is if for some reason this limit was equal to a value other than 1, let's say this limit was equal to 1/2, you would have the absolute value of x divided by 2. Then you would have to multiply both sides by 2 so that you would just have the absolute value of x less than some value. In that case, we would have 2, and so the radius would be 2. Okay, so I just wanted to make that clear that that is how you determine what the radius is for a power series when you get to this point. And so I'm just going to make a note of that up here. The radius is equal to 1. And so now, if we look at what values of x make this statement true, another way to rewrite this, the absolute value of x less than 1, is to say that x will be less than 1, but greater than negative 1. Right? That's what these absolute value bars are saying, that for any value of x from negative 1 to positive 1, the absolute value of that value will be less than positive 1. Okay? And so what we find here is that when the value of x is between negative 1 and positive 1, this series is a convergent series. So if x equals 1/2, this series would be convergent. If x equals 1/3, this series would be convergent. If it equals negative 1/4, it would be convergent. But if it equals 2, it diverges. If it equals 3, it will diverge. Or if it equals negative 10, it will diverge, because those values would be greater than 1 or less than negative 1. All right, so any value of x between negative 1 and positive 1 will make this series convergent. The only thing we're not sure about here are these endpoints. We don't know if this power series will be convergent or divergent for negative 1 or positive 1, right? We're saying that when x is greater than negative 1, not greater than or equal to, and when x is less than 1, not less than or equal to. All right, and so the ratio test is inconclusive for those two values. And so what we have to do is test those two endpoints to actually get our interval of convergence. All right, because right now we would say that our interval of convergence is from negative 1 to positive 1, but we don't know if those two endpoints should be included or not. We don't know if we should have closed brackets instead of open ones. And so what we will do is use those two values of x for our series and see if that series converges or diverges. We're going to manually check those endpoints. All right, and so if I clean up my work, let's start by checking x equals negative 1. Here's how we're going to check that. We are going to look at this series where x is equal to negative 1, right? So we would have the sum from n equals 1 to infinity of negative 1 to the power of n divided by n. We just replace x with negative 1, and now we have a series that we can determine the convergence or divergence of. If we find that this series is a divergent series, then we will keep that open bracket open. Negative 1 will not be included in the interval of convergence. But if this series does converge, then we will make that a closed bracket, because then negative 1 is included in the interval of convergence. Okay, and so if we look at our series here, we have an alternating series because we have negative 1 to the power of n in the numerator, right? And so what we can do to determine the convergence of this series is use the alternating series test. At this point in the problem, you're going to have to use other convergence tests that we have gone over for series to determine if those endpoints should be included in your interval of convergence. All right, so in this case, we're going to use the alternating series test. And remember, the alternating series test says that our series will converge if two requirements are met. The first requirement is that the limit as n approaches infinity of the sequence a sub n needs to be equal to 0. And remember that that sequence a sub n will be the sequence from our series without the part that makes it alternating. So in this case, we're just looking at 1 divided by n. We remove the negative 1 to the power of n and just have 1 divided by n. All right, now the limit as n approaches infinity of 1 divided by n is going to be 0 because 1 divided by infinity is 0. And so that checks out. Our first requirement is met for the alternating series test. And so then we can check our second requirement, which is that this sequence needs to be a decreasing sequence. In other words, a sub n plus 1 needs to be less than or equal to a sub n. In this case, that would be 1 divided by n plus 1 compared to 1 divided by n. And so is this term always less than or equal to this term? And what this means is that the next term of this series is less than or equal to the previous term, which means that that sequence would be decreasing. That's what we're trying to show here. And so since this denominator of this term is always going to be 1 greater than this denominator, right? We have n plus 1 compared to n. The value of this fraction will always be smaller because when you have a larger denominator for a fraction, that value gets smaller. All right, so 1 divided by n plus 1 is less than or equal to 1 divided by n, which means that our sequence is decreasing, and so both requirements for the alternating series test are met, which means that this series is a convergent series. Our power series, when x equals -1, converges. And so we can go back to our interval of convergence and change that open bracket to be a closed bracket. We are now including -1 for that interval of convergence. Okay, so now we have checked one of the endpoints when x equals -1. Now we need to check the other endpoint when x equals +1. So when x equals +1, we will have the sum from n equals 1 to infinity of 1 to the power of n divided by n, right? We just replaced x with 1. And 1 to the power of n, as long as n is finite, is just 1. And so we can just remove that n. 1 to the power of anything is just 1. And so our series is the harmonic series where we have the sum from n equals 1 to infinity of 1 divided by n. And we know that the harmonic series is a divergent series because it is a p series where p is equal to 1. The power of n is 1, and so this series diverges. All right, so when x equals 1, our power series is a divergent series, and so x equals 1 will not be included in the interval of convergence. We will leave that bracket open. All right, so our interval of convergence is from -1 to +1, including -1, but not including +1. All right, and so that is the interval of convergence. And this is our radius. The radius is 1 because this power series is centered at 0. And as you can see, the endpoints of the interval of convergence are both 1 away from that center of 0. Okay, and so this was our final example. This showed you the third way that a power series could converge. Just as a summary, the first way was that the power series could converge for one value of x only when x equals c. The second way is when the power series converges for all values of x, and the third way is what we found right here, where the power series will only converge for values within a certain radius. In this case, that radius is 1, and our interval of convergence is from -1 to 1, including -1. Okay, and so with that, this is all I had on power series. So if you want to see some more examples of determining intervals of convergence, as well as the radius for a power series, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.